Okay, so going through this, I'm going to just give you the answers. I'm not going to go through how I got the answers, because when we take a look at each of these molecules here, we would either have to do the replacement test to figure out how many signals there are. We would have to do the planes of symmetry, axis of rotations. So I'm just going to go through it fast, and if you need some help on why the answers are the way they are, then please feel free to come chat with me or one of my ULAs during office hours. Okay, I'm just trying to get my notes here. So just get... Okay. So let's take a look at that one right there. How many signals are there going to be? Well, we have our methyls. And then we have these two protons. And so those are going to be equivalent to one another. And then those are going to be equivalent to one another. And so we need to be able to now predict the splitting pattern of these. And A is going to be split into a triplet, and B is going to be split into a septet. So that's a simple splitting pattern right there. If we come here to this one, we need to draw out the hydrogens. Now, if you do the replacement test, you will find that these three protons are all diastereotopic to one another. Or said more accurately, they're all non-equivalent to one another. C and B are diastereotopic to one another. So what we have here, okay, is A is going to be split into a doublet of a doublet. And B is also going to be split into a doublet of a doublet, and C, doublet of a doublet. Now, I would like to go through that one. So let's just look at proton C. Why does that get split into a doublet? Well, the first thing that we do is we find the carbon it's directly attached to, the hydrogen is directly attached to, and then go to the adjacent, and we see that there's one proton. So that counts for the first doublet. But with alkenes, we have to expand that rule to say, hey, this HB right here, yes, it's attached to the same carbon as proton C. However, proton B is not equivalent to C, and so it's within 3 bonds, so it's going to couple. And so HB is going to couple HC with the other doublet. And so the answers for the splitting patterns for A and B are the same concept as well. Okay? So that's 3 signals, and each of those signals would be a doublet, doublet, doublet. Now if we take a look at this one right here, let's just make sure we understand that those are methyls. We have our wedged and dashed hydrogens right there. Now, so what's the relationship between these proton groups right here? We'll call that guy B and B. Those are equivalent, and then all of these are A. They're all equivalent to one another. So A is going to be split into a quartet because the adjacent carbon has 3 protons. And then B is going to be split into a triplet because the methyl groups are going to be split by the A protons, and there are 2. So if you focus right on that right there, do you see how this carbon is adjacent to that carbon and there's only 2 protons there? So 2 plus 1 is 3, making that a triplet. Okay, so this one's a complex splitting pattern here. And we have to be very, very careful and realize that we have a stereocenter. Okay, when we add stereocenters, things are not as simple as we would hope. So there's a proton coming off of there, wedged, dashed, and there's our other methyl. So what is the splitting? How many signals would we expect for this guy? Would A, B, C, D, E, and F. So that's 6 signals. 6 signals. Now, a lot of people will say, hey, those protons are equivalent to one another, but they're not. They're diastereotopic to one another. And so that's going to give 2 distinct signals there. So if we take a look at A, what is the splitting pattern for A? That will be a singlet. B will be a doublet of a doublet, because B is attached to that carbon, and the adjacent carbon would be this guy. There's no protons there. We do not couple to this proton because it's attached to a heteroatom. And then the adjacent carbon that I just highlighted there has 2 protons. So the common mistake would be, hey, that should be a triplet because 2 plus 1 equals 3. But that's not true because protons E and D are not equivalent. So you have to look at them separately. So proton E, there's only one of them. So 1 plus 1 is a doublet. And then HD, there's only one of those. So 1 plus 1 is a doublet. So B gets split into a doublet of a doublet. Now the proton C, that would be a broad singlet because of all the hydrogen bonding network there. And sometimes in the NMR spectrum, this proton right here gets completely replaced with deuterium. And so you may not even see a signal for that proton. Proton D, right there. That's a complex splitting pattern now, okay? So if we go with blue, proton D is attached to that carbon that I highlighted in blue. What's adjacent? This guy's adjacent. And how many protons are there? Only 1. So 1 plus 1 makes that a doublet. But then we also have to go to this adjacent carbon right there, and there's 3 protons. So 3 plus 1 is a quartet. So we could say a doublet of a quartet, but then we have HE, which is attached to the same carbon as HD, but it's not equivalent. So we have to treat it as such. And there's only one E, so that 1 plus 1 makes a doublet. So we have a splitting pattern of that's called a doublet of a quartet of a doublet. You could have said a doublet of a doublet of a quartet. I don't care how you mix those up, but it would be just fine. As long as you have that splitting pattern right there. Okay. Okay, so what's the next one? E. So E is going to be the exact same thing as D. So a doublet of a quartet of a doublet. Same thing. And then F. Where's F? This one is F. We go to the adjacent carbon. So that would have to be a doublet of a doublet. Okay. How many signals for this guy? First things first, draw in all your protons. There. We've seen this molecule before, so we can predict its splitting patterns, or sorry, how many signals. So that's A, B, and B, and then C and C. So there's going to be 3 signals, and the splitting pattern for A is going to be a triplet of a triplet. Okay. And B is going to be a doublet of a doublet. And C is also going to be a doublet of a doublet. Okay, so this problem right here, this one's going to have a complex splitting pattern as well. So our methyl okay, splitting patterns here. So those protons are A, B, C. Those are equivalent, and E. So how many signals would we expect? 5. So the splitting pattern for A is going to be a triplet. B is going to be a quartet. C is going to be a triplet. D is going to be a triplet of quartets. And E is going to be a triplet, like that. Let's focus on D real quick. Why is that a triplet of a quartet? Because there's the carbon that it's attached to. What's adjacent? That one. How many protons are there? There's 2 equivalent protons. So 2 plus 1 makes a triplet. And then we have an adjacent carbon right there. And there's 3. 3 plus 1 is 4, making it a quartet. So that's where the triplet of quartets comes from. So A, B, C, and E are all simple splitting patterns, but HD, that's a more complex splitting pattern. Let's see, next one. So in this particular one, it might be a good idea to like redraw this molecule to help you see the plane of symmetry. So we also have a proton coming off of there, and we know that the methyl, the hydrogen, or that methyl and that methyl and that hydrogen, they cannot all be in the same plane, right? So if we think about it and redraw it, we could envision something that looks like this. And maybe that's a little bit easier for you to see the plane of symmetry now. And so if we look at the signals, that would be A. These 2 protons that are coming off of here, right there, those are going to be B's. Those are equivalent. Then we have C and C, and then D, like that. So A would be a singlet. B would also be a singlet. C would be a doublet. And D proton. Now this one trips people up. The D proton's attached to that carbon. So what's the adjacent carbon? That one and these two. And so those two right here, they're equivalent. So there's a total of 6 protons. Okay? 6 plus 1 is 7, making that a septet. Like that. Pretty slick. Okay, this one here, we know we have a methyl with dashed hydrogens, and those are attached to sp2 hybridized carbons, so those have to be in the plane. And we're going to see that those protons on the alkene, they are not equivalent to one another. They're distereotopic, so non-equivalent. But these are going to be equivalent to one another because there's going to be a plane of symmetry and then those methyls right there. So A is going to be a doublet. B is also going to be a doublet. C is going to be a singlet. They don't have any adjacent carbons with protons on them. And then D is also going to be a singlet. So a very simplified splitting pattern for that molecule. Okay, so this one right here is a little bit more complex. But using the principles you've been taught, we can figure this out. There's a proton there and a proton there. So if we label these, this would be A, B, C, and D, because we have a stereocenter now that we have to factor in. And so we have A, B, C, D. Those two protons are E, and those would be F. So if we take a look at this, how many signals are there going to be now? 1, 2, 3, 4, 5, 6. What? Well, gotta be careful. Not 6, because what's also here? There's a proton right there. So A, B, C, D, E, F, G. So there's 7 protons, or 7 signals. So if we look at A is going to be a doublet. B is going to be, this one's a complex one, because B is attached to that carbon. What's adjacent? That one. And there's only one proton, HA, so that would be a doublet. And then we have this adjacent carbon right there, and there's 2 protons, so it's very tempting to say a doublet of a triplet. But why is that not accurate? Because the 2 protons are not equivalent. It's proton C, proton D, so you have to treat them separately. How many C protons are there? Only 1. So 1 plus 1 is a doublet. So we have a doublet. That's for the C proton. But now we have a HD proton. How many D protons are there? Only 1. So we have a doublet of a doublet of a doublet. And you could just write it like this if you'd like. We could just say, hey, let's make life a little bit cleaner. Just go doublet, doublet of a doublet. C now. That's another complex splitting pattern. Because C proton is attached to that carbon. What's adjacent? That one. And there's only 1. So that's a doublet. But then we have to go to the other adjacent. And there's only 1 proton, Hg. So that's a doublet. But then we have HD, which is attached to the same carbon, but it's not equivalent. So that would also split into a doublet. So proton D would be the same answer as C, same connectivity there. Right, doublet, doublet, doublet. E, that's just going to be a singlet because protons attached to heteroatoms don't couple. Right, F, that is a singlet as well. And then A, B, C, D, E, F, G, G. Okay. What's that going to be? Well, we're attached to that purple carbon now. Hg is attached to that. What's adjacent? That guy. And so those are two non-equivalent protons, so that would be a doublet of a doublet. CH3. So this one, did we not already do that one? No, I guess not. So we could say A, B, C, D, and E. So 5 signals. So A is going to be split into a doublet of a doublet. B is also going to be a doublet of a doublet. Proton C is going to be way more complex because C is attached to that carbon. There's an adjacent. And we have two non-equivalent groups. So HA is going to split into a doublet. HB is going to be, or sorry, HC is going to be split by HA as the form of a doublet. HC is going to be split by HB in the form of a doublet. But HC's carbon is also adjacent to that one. And there's two groups of equivalent protons. So 2 plus 1 is 3. So we have a doublet of a triplet. And ABC, now what's D going to be? D is adjacent. There's D. We're adjacent, no protons. Adjacent, only one proton. So that's going to be a doublet. And then E, the carbon that the protons are attached to, is that one with adjacent carbons right there. 0 protons, so that has to be a singlet. This triangle one, just make sure we realize that we have those protons there and those protons there. So those are equivalent A and A, B and B, and then C and D. So we have 4 signals. So A is going to be split into what? That's going to have to be a, so wait, what did I say? Sorry. A, okay, so A, the protons are attached there, so we have to go adjacent, and there's only one proton. Okay, so A is going to be a doublet. B protons are attached. The B protons are attached to that carbon. What's adjacent? This guy. And there's 3 protons there, so that's going to give it a quartet. And then that's also adjacent. And there's 2 non-equivalent protons. HD will split HB into a doublet. And then HB is going to be split by HE as a doublet. So what we have is a quartet of a doublet of a doublet. Okay, proton C. Proton C, let's use green, is attached to that carbon. What's adjacent? Those are both adjacent to it, okay? So there's 2 equivalent protons there. So that's going to be a triplet. 2 plus 1 is a triplet. But HC is also right attached to the same carbon as HD. And there's only 1 D proton, so that's going to N plus 1, or 1 plus 1 is 2, making that a doublet. So you could say triplet of a doublet or a doublet of a triplet. And proton D right there is going to be the same as C. Triplet of a doublet. Okay. Okay, let's approach this matching problem now. Now, all of these problems right here, we've already established how many signals they would get and their splitting patterns above here. So what we need to now do is look just at the spectra and annotate the spectra, and then we compare and see the matches. So first thing that I like to make sure I understand about a spectra is that these numbers right here, that's the integration. So that's telling you the ratio of the protons. So if you add up all those values right there, so we have 6, 9, 10, 11, 12. If you go and look at all the molecules up here, if your molecule has less than 12 or significantly more than 12, then the odds are it's not the right molecule. So you can use integration as process of elimination as well. Another thing that you need to look at is how many signals are in the spectra. Well, there's there's 1, 2, 3, 4 signals. So when you have 4 signals, when you come back up here to what we've evaluated so far, any molecule that has more than 4 signals is off the table. So for example, problem 10 is no good because it has 5 signals. Problem 9 has more than 4. So those are just, we don't even need to look at those because the NMR or the spectra says, hey, we have a molecule with only 4 signals. Then the next thing that you need to take a look at is the splitting pattern. So that guy is a singlet, that's a singlet, that's a doublet. Now this guy right here, because of the resolution, isn't as good as I'd hope it is. So zoomed in as best as I have it there, you see 5 peaks, possibly 7. Okay, so right now I'm going to say, let's say a pentet or a septet. That's kind of hard to tell, but we're just going to put that out there. Okay, now we have everything identified to the best of our ability. Now we just have to go back and match now. Do we have a molecule above that has 2 singlets and a doublet and possibly a pentet or septet? So if we go through here, we look at this information right there, and that's clearly not matching our splitting pattern. So 10 and 9 are off the table because there's more signals. 8 has 4 signals, but that has a doublet, doublet, singlet, singlet. So that can't be a match because when we go back to the spectra of interest, we have something down there that's more complex than that. So that molecule that we just looked at, so number 8, that's off the table. The splitting pattern doesn't match. But now we take a look at this guy right here. Number 7 does match pretty well. We have a septet, doublet, singlet, singlet. Do we have anything else that matches that? No, we don't. So that's our best option. However, we need to be able to annotate the NMR. We can't just say, oh, that's a match, and we're going to call that good. Okay, so what we have to do is take that molecule that we found, let's see, let's go back here. So how do we copy and paste here? Let's try it again, shall we? I guess we'll have to paste it and then just drag it, looks like. Okay, let's try that. That's cumbersome, isn't it? Maybe we'll just have to redraw it. That will probably be a whole lot faster, won't it? Okay, so if we have our molecule here, you know, let's just redraw the darn thing. This is silly. So our molecule looked like this. Right there. And when we've annotated it, okay, we said, we'll call that A, we'll call that B. The proton coming off of here will be C, and then D and D. So A and B are singlets. Which one would you correspond it to? So is this signal right here, is that A or B? Well, two ways you can look at it here is B is attached to a oxygen and a carbonyl carbon. So that's going to be way downfilled. Whereas A is only attached to an oxygen. So between those two options, B should be further downfilled. So I'm going to say this proton, or this signal right here, that's B. And then this one would have to be A. Because those are the only two singlets possible, because A is a singlet, B is a singlet. C, on the other hand, is what? That's going to be, hey, there's 6 protons, so that's a septet. And then D is going to be a doublet. But if I go back between A and B, how can I also distinguish why I labeled those B and A? Look at the integration. 3 protons. A has 3 protons. B has 2 protons. So that all matches up. And then how would we label, where is C at? What signal corresponds to C? Well, C is a septet. and that is a septet. So C is right there. And then D is a doublet. There's our doublet right there. So when you are looking at NMR spectra, you have to annotate it. You have to draw the molecule, label all the signals on the molecule, and then correspond that to the spectra. It's not going to be good enough just to match the spectra. Okay, let's take a look at number 13. 13 has two signals, integrates for 6 and 4. We have a triplet and a quartet. So if we take a look at this molecule here, we will see that we have signal A, and then B and B. So A gets split into a triplet, and B gets split into a quartet. So B and A, like that. And in class today and in this video, I kept calling it a pentet in this example. Shame on me. When there's 5 signals, or a signal is split into 5 peaks there, we call that a quintet. So my apologies for that. Okay, number 14, we also have 2 signals. Okay, and what does that integrate for? That's 6 and 2. Okay, so that looks like a triplet. Okay, and this one, how many signals are there? 1, 2, 3, 4, 5, 6. And it's kind of hard to tell what that is, but we kind of get a rough idea. And so that would be, what, 6 signals there? 1, 2, 3, 4, 5. No, I'm counting 6. So we call that a septet. And when we take a look at this molecule here, you see we have signals there and there. So A has a total of 6 protons, which matches that. A also splits into a triplet, so that signal is A. And B splits into a septet. Because, why does B split into a septet? Because we have those methyls there. And so those are equivalent, and the 2 protons here, which are called B, are going to see 6 total equivalent protons. So 6 plus 1 is 7, giving us a septet. And it's really hard to see 7 signals in there. But that's kind of the challenge, though, of NMR a little bit. The resolution sometimes isn't as good as you would hope it to be. Now, when we take a look at problem 15, those look like singlets with the resolution that we have, but we have this right here, which is a zoomed in view of it. And we can see on the zoom in that those are going to be doublets. And this is going to be a singlet and a singlet. We have a singlet that integrates for 3, a singlet that integrates for 2, and then 2 doublets that integrate for 1. So the molecule that matches that spectrum right there would be this guy right here. We're double bond there.
So
Okay.
we lose lose that DNA, then we lose the ability to write what we said, right?
So how many signals are there in this molecule? We have A, B, C, and D. So we have 4 signals in the predicted, when we're predicting how many signals. And then we see 4 signals in our NMR. And A is going to be split into a doublet. And B is going to be split into a doublet. C is going to be a singlet, and D is going to be a singlet. So now we just need to figure out where those go. If we start off like this, we would say, hey, which singlet is D? Okay, so an easy way to do this one would to help, what will help us is the integration. There's 3 protons, and so there's 3 protons there, so that has to be signal D. And proton C, there's only 2 of them, which matches that integration, so C would have to be that signal. Okay, and then now we have our doublets that we need to account for. Okay, and so when we take a look at A and B, where would those signals show up? Which one would be further downfield? Now when comparing A and B, which one's going to be further downfield? Well, B is going to be further downfield because when you take a look at the electron cloud of bromine and the electron cloud of the B proton, do you see how they're really close to one another in comparison to A? And so there's going to be some more de-shielding due to proximity effects from that bromine. And so A is going to be right there. But that one was a little bit of a tricky one. Okay, so let's take a look at 16. When we take a look at 16, what do we notice here? Okay, 16, we have a singlet.
Hello.
We have a singlet right here. And what does that look like? A doublet. And then just in here, that's just like a mess. Okay, a lot of going on there. Okay, question number 17. What do we have? A doublet, and let's see here. Wait, oh, we have to zoom. Do we have to zoom in? No. Oh, sorry. Yeah, when we look in, zoom in, those were not doublets. Those are doublets of doublets. And that would be doublets of doublet as well. When we zoom in a little bit better. So the only molecule that matches that would be this guy. Okay, because if we go A, well, let's change the color here. If we go A, B, and C, A is a doublet of a doublet, B is a doublet of a doublet, and C is a doublet of a doublet. Okay. Now, which one would, where would be, and this one also we're going to need to have like 100% confidence, you would have to look at some J coupling. But let's give it a try and use the principles that we've learned up to this point and see if we can figure something out. Okay. So when we take a look at this, which hydrogen would you expect to be the furthest downfield? You would expect A to be the furthest downfield because it's connected to the same carbon that the bromine's attached to. And then based off of my last example, you would expect C to be the next, and then B, and C because electron cloud are really close to one another. So that's how you would predict those chemical shifts for that one. Okay, last one, I believe. Yeah, last one. So, ooh, this one's a lot here. So we have a triplet there, triplet there. 1, 2. Ooh, that's hard to see, isn't it? 1, 2, 3, 4, 5, 6. So let's hold off on that one for a moment because that's kind of hard to see. 1, 2, 3, 4, 5, 6. So maybe a quintet because I see 6 signals. And then we have a triplet there and a quartet there. So the answer to that one would be this guy. Like that. Because we have signal A, B, C, D, and E. A has to be a triplet. B has to be a quartet. C has to be a triplet. D has to be a quartet of triplets. And E would have to be a triplet. So we have, what, 3 triplets we have to distinguish here. And then we have, yeah, three triplets. So what do we do here? How would I approach this? Well, there's only one thing that has a quartet. B is a quartet. Okay, so that would have to be this signal right here. So B is for that guy. So that one's done. And then here in the middle there, that's the messy one. That's the quartet of triplets. Okay. And so when we do a splitting tree for that, what would we expect? Would we expect a quartet of triplets to look like? So if we have the signal HD, okay, and I split that signal into a quartet, I would take that signal and split it into 4 signals. And then you would take those 4 signals and split those into triplets. Like that. And so we would expect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. But we have a lot of overlap going on here. So we don't have 12 peaks right here because we're going to have some overlap between these. And so that's one unfortunate thing about it, that sometimes when you predict how it should be, it's not going to look that way because of overlapping of signals. But in this simple molecule here, that quartet of triplets makes sense. Okay, it's the only other signal that could possibly go for that. So we would say that would be D. Okay. Now, how the Klein textbook teaches it, though, it will make a little bit more sense in the fact that it views these D protons right here. It's going to take a look at these protons right here, okay, and then these protons right there. So the way I've taught you how to predict a splitting pattern right here, that's how it should be done. That's the predictive manner. But Klein also teaches it where you don't worry about if the hydrogens are not equivalent or not. They just say, add up how many hydrogens are adjacent to that carbon. So adjacent, there's 2. And then that's the adjacent, and then there's 3. 3 of them. So that's a total of 5 protons. 5 plus 1 equals 6. Okay, so you would expect, based off of using that logic, you would have a sextet. And I guess if you zoom in really carefully, you could see 6 signals right there. Okay. Okay, so let's keep annotating this. What do we have? We found signals B and D. Now we have 3 triplets. Okay. So we see that proton C gives us a triplet and it's right next to a carbonyl. B gives us a quartet. So we've already figured that one out. We've already figured out D. So C is a triplet attached right next to a carbonyl. So that has to be the one furthest down filled amongst the triplets. And then we have 2 triplets left. We have A and E. Which one is closest to the carbonyl? A is. So A should be downfilled compared to E. And so that's how you would annotate that NMR. So I hope that answers your questions, and if you need any additional help with that, please let me know.